Hi, everybody. I'm going to go through a little overview of the SN2 and E2 reactions that we started talking about. So for SN2, okay, we're just going to do a side-by-side comparison of the SN2 and the E2 reactions so that you can kind of see where they overlap and where they diverge from each other. So basically, you have the same starting materials, and you can get both SN2 or E2 or both of them. So the first thing that I like to look at is I just like to identify what kind of alkyl halide I'm using first. So this one, because I've got this carbon attached to two other carbons, this is a secondary alkyl halide, which I usually just annotate like that, okay? Then I look at my nucleophile. I've got sodium methoxide and I've got methanol on my arrow here. Methanol is just the solvent. It's just what's allowing us to stir this because sodium methoxide is a solid. And then the sodium methoxide is going to be my strong nucleophile. Okay, so I really have a negative charge on that oxygen, positive on the sodium. So my nucleophile is going to come attack my electrophilic carbon, and then my leaving group is going to get pushed off. Okay, and as we do this, we want to keep in mind that the bromine, if it's pointing away from us, then our methoxide is going to come from the front, which is the opposite side of the leaving group. And so now we're going to end up with inversion of stereochemistry here, and that OME is going to be on a wedge. Okay, so I'm going to get that product out. And nothing happened to my stereocenter on the other side. It is just the way it is. Okay, so then if we change our attention over to the E2 side, okay, again, same starting materials, everything is identical here. So E2, we're looking for anti-periplanar, right? And we're looking for beta hydrogens. So the alpha position is the one that has the halogen on it. And then the beta is going to be anything that's directly attached to the alpha. So in this case, I've got two beta positions. And then I just like to go in and draw all of my H's. Okay, so once we get here, I've drawn in all the beta hydrogens. I've got my beta carbons labeled. So now I'm looking for any H's that are anti to my leaving group. Okay, so this H and that bromine are both on the same side. Those are cis to each other, right? Or syn. These two H's, that H and the bromine are syn, but this H and that bromine are anti. Okay, so we're looking at this H, and that's the one we're going to take. So we're going to go grab that H. Electrons move over to form a pi bond. Bromine gets kicked off. And we end up with our product. And that's the only product that we're actually going to make for the E2 side. Okay. So one thing to keep in mind here is if we look at the chair, I've got methyl up, bromine down, do my flip, and then I've got methyl up, bromine down. So in these two chair conformations, when I have my bromine equatorial, we actually cannot do an E2 reaction when the bromine is in the equatorial position because we are not able to get anything anti to it. We can't get any H's anti. So this is not going to actually do a reaction. Okay, and I'm going to make this more general. We're going to say equatorial leaving group. Okay, so it's only when the leaving group is actually in the axial position, then you can see that when I have my H's drawn in here, that H, the one that's up, is the H that's actually anti to my bromine. Okay. Okay, so now that we have the reactions drawn out, let's just go through and just kind of note down some of the similarities here. So the first thing that I want to look at is just the reaction coordinate diagram of these two reactions. Okay, so I'm just going to draw a reaction coordinate diagram real fast. Okay, so we've got energy over here. reaction coordinate down here. Okay, so both of them have the same starting material. So we're gonna just have same starting material here. I tried to get at the same energy, but I mean, everything is all crooked here anyway, so it's fine. So I've got my reactants. Okay. Same energy levels. And that includes all three of these. So it's going to be all of them that are kind of taking that into account. So I'm actually going to raise it up a little bit so that we're accounting for the O minus though, the methoxide. Okay, and then we're going to products that are lower in energy because we're taking care of the negative charge on the OMe. We're switching it out for a Br minus, which is going to connect to the sodium. So we're going to make a sodium bromide salt. And then everything's going to be pretty well neutral and stable. So we're going to be going down in energy here. This one, we are still going down in energy because we're getting rid of the OMe here. So the two products may not be exactly identical energy, but that's okay. This is just a quick little guess. Okay, so I've got my reactants, I got my products. I only have one transition state denoted by the fact that I've got one arrow here. I've got no intermediates in between them. So both of them are going to just do the single dip up or slide up and then dip down. Ooh. Freaked myself out with the chairs that are so close there. Okay, and then we end up getting the same reaction coordinate diagram. So the reaction coordinate diagram is being very, very similar. Is something you want to think about that, oh goodness, why am I just not working with this? Okay, that's better. So the reaction coordinate diagrams being very similar is something we want to consider because they are both a concerted mechanism. So we're going to have mechanism. They are both concerted. Okay, and concerted just means all one step. Okay, so we have our bonds forming and our bonds breaking all at the same time. All right, so that's the mechanism. So if we think about the electrophile and what kind of what happens when we switch the electrophile up here. Okay, so we're going to be looking at primary, secondary, and tertiary alkyl halides. So I'm just going to label those RX. And then same over on the other side. Okay, so as we talked about in class, the primary is going to work great for SN2. It's not going to work great for the E2 because the SN2 and the E2 are going to be fighting it for it quite a bit. So this is going to be okay. Okay. It's, well, I'm going to downgrade that to, yeah, we'll keep it okay. Okay, so generally the SN2 is going to win out when you've got a primary alkyl halide. As soon as you move to secondary, though, now the SN2 is going to become a much harder accessible electrophile for a nucleophile, but it's going to be much, much better for an acid-base reaction where you can just kind of like grab a proton. You don't have to go in that far. So this is going to be good for E2. Once you get to tertiary, this is not possible. Okay, SN2 on a tertiary alkyl halide is not going to happen, but it can still do an E2 just fine. Okay, so those are the things that we want to keep in mind here. As steric interactions go up, SN2 goes down. Okay, so SN2 does not like crowded electrophiles. Okay, that's going to be our take-home message here. So the more crowding we have, the less SN2 product we're going to get. E2 is fine with crowded. All right, so then let's move on to the nucleophile. And we're going to say nucleophile / base. And I'm going to keep the list on this video very short because I'm going to go over a couple of other videos that focus on SN2 or E2 alone. And I'll give you a list of nucleophiles that will enable you to kind of select one or the other. Okay, so for this list, we're going to keep it simple. So OH minus, OME minus, and OET minus. Okay, both of those are going to allow us to do the reactions we've talked about in this video so far. Okay, they'll both be able to do SN2, they'll both be able to do E2, and you're really more relying on your alkyl halide to tell you what's going to happen. Okay, so if we look at stereochemistry next, I would say this is one of the big differences. Okay, so stereochemistry for SN2, as we saw up here, we get inversion of that stereocenter as we attack from the opposite side with our nucleophile, versus E2, we're looking for that anti-relationship here of our leaving group and our proton. So over in the SN2 side, we've got inversion. Over on the E2 side, we need to have anti-periplanar H and leaving group. Okay. So then if we look at kind of major products, this is just basically, I just want to summarize kind of what we've already discussed here. So SN2 is going to be the major product when using a primary alkyl halide with the nucleophiles listed above. Okay, and then E2 is going to be the major product when using a secondary or tertiary alkyl halide. Okay, so that's what we're looking for. The E2, as we've seen, we can get a whole bunch of different E2 products. So the way that we decide which of those alkenes is the major product, we're looking for a more substituted alkene. Okay, that's actually going to be a more stable alkene, so we're looking for a more stable product, and we want trans over cis. Okay, so trans alkene, where you've got them staggered, is going to be much more stable than a cis alkene where you've got them eclipsed. Okay, so let's look at a couple of examples, just kind of pulling all this together. So first example, let's look at just this 2-chlorobutane with sodium hydroxide. Okay, so I'm just going to have all the products listed up at the top just as a summary, and we're going to go through them one by one down below. So first up, I always like to start with the SN2 reaction just because it's the easiest and I get it out of the way quick. So SN2, we're going to start with our alkyl halide and our nucleophile. Okay, OH minus is our nucleophile here. I'm totally fine if you just drop the sodium or the counter ion or whatever. It's just a spectator. It's not actually doing anything. So because I've got my chlorine pointed towards me in the front, that means the OH minus is going to have to come from the back. And I'm going to pop off my chlorine leaving group. I get my inversion here, so OH minus approached from the back, so now it's on a dash. I've made NaCl. Again, I don't really care if you draw that out. So then my SN2 product is going to be that. Okay, I'm formed an alcohol, it's now on a dash. So now my E2 products. So now I'm thinking about my OH minus as a base, not a nucleophile. So let's go ahead and start by labeling out the alpha position and then the beta positions. Okay, and then drawing out our protons. Okay, so I have 2 beta positions, 5 protons in total. So I have a potential to have up to 5 E2 products. But we need to make sure that we're thinking about this carefully. So I'm going to go ahead and start with the beta position on the left. So we're going to go, sorry, I'm going to get that duplicated now. So we're going to start over here. I'm grabbing the H that's on a dash so that it's properly aligned with the chlorine. And then we form that pi bond from the CH bond electrons, kick off our chlorine. And again, we're going to keep the backbone of this the same here. Okay, not moving that at all. And that gives us a pi bond right here. Okay, so the thing we want to keep in mind is if I had rotated this to get one of these other 2 H's in the dash position, would this alkene have changed at all? And the answer is you can rotate around this bond and not change the carbon chain at all. Okay, so for this side, I really only need to look at one of those protons because it doesn't matter which one you take of the 3, it's all going to be the same rotation or the same conformation. Okay, so now let's look at the right-hand side, the right-hand beta. So right now I'm going to have, let's just label this as A and B. Okay, so right now HB is properly lined up. That's the one that's currently anti. So I'm going to go grab that proton with the H, form the pi bond, kick off the chlorine. Again, we're keeping the carbon chain the same. I have not done any rotations yet. And then we end up with that pi bond. Okay, so this has made a trans alkene. All right. So then let's look at what we need to do to get HA. I should have copied it, but let's. Okay, so we've got A, we've got B. So we already saw the product from B. So let's go ahead and do a bond rotation because we need to rotate it in order to get the chlorine and HA in the anti-conformation. Okay, so my first move here, I'm just going to keep the left-hand side of the molecule the same, so I've not touched the other side, and I'm just going to twist that methyl group to be down. So we go down, and that's going to push my H's around. So now HB is going to be on a wedge, and HA is now on a dash. So now my chlorine and my HA are anti. So we go grab HA, form our pi bond, kick off chlorine. And again, we're going to keep the backbone of the carbon chain the same as how we left it, how we did the arrows on it. And now I've got my pi bond there. Okay, so this is going to be the cis. All right, so I have 3 different alkenes. So I'm going to go ahead and add these up here. Okay, and I'm going to erase the, there we go. Okay, so I have these 3 products. So when we're talking about substitution of alkenes, we're thinking about how many carbon bonds do I have attached to the alkene. So this would be a mono-substituted. these are both di-substituted alkenes. Okay, and I'm just gonna mark down like that's the substitution, that's the substitution, that's the substitution. Okay, we've got 1 carbon versus 2 carbons versus 2 carbons. Okay, so then that means that these are more substituted, but overall, this trans alkene is going to be my major product. Because it's the most substituted and trans. Okay, so it's the most stable of all the alkenes possible. So because we've got a secondary alkyl halide, that's going to make E2 our major product. And then this alkene is our major product because it is trans and it is di-substituted. Okay, so it has the most amount of substitution and the stablest conformation. Alrighty, so hopefully this was helpful. We will keep on practicing these and let me know if you have any questions.